part 4 of the Neurips discussion. In this episode, I'm going to talk about DeepMind, mainly work of DeepMind. And what's really fascinating to me about this work is the way they try to self-referentially improve systems. So they try to use evolutionary algorithms or sort of self-referential feedback loops where, let's say, large language models write code and then improve that code based on some certain selection criteria. I think what DeepMind's trying to do here is deeply rooted in work that goes back to Gödel, Church. People like Schmidhuber have taken that work later on, sort of in the 90s, and used it as an exemplar for self-referential systems that can continuously learn and get better, and therefore, in my opinion, mimic intelligence the way at least we here at Orange Capital Partners see intelligence. Well, the way we look at intelligence is not something fully developed and there's this AGI and wow, we have it, right? It's not going to be like that at all, no matter how much marketing machine BS is coming out of certain companies. What we're looking for is the agent that has a certain set of parameters and algorithms that allow it to learn, and also is exposed to the right data, of course, that can help it learn. I mean, this is really the key. We've spoken about Datacom, for example, a project out of UW where you're sort of questioning the central dogma of machine learning, or AI, if you will, which is data, model, algorithm, and you can flip this around. So each one of these three sections can improve. And I think this work by DeepMind, I'm going to go through all of them. We're going to talk about Promptbreeder, Self Debugger. We're going to talk about Chain of Code, FunSearch. Then we're going to talk about the robotics endeavors, in particular RTX and OpenX. And then finally, we're going to talk about a paper that is not fully related to the sort of self-referential improvement literature out of DeepMind, but it's also a paper out of DeepMind, Understanding Diffusion Objectives as the ELBO with Simple Data Augmentation. The fundamental idea here is that you can look at diffusion models, which are sort of vector gradient type optimization models. You can compare them to maximum likely estimation, sort of traditional probabilistic modeling type assumptions, and at the sort of at the limit, those two converge, and having a conceptual understanding of what a maximum likelihood estimation looks like and what a diffusion model looks like, and kind of comparing them, I think gives some really good insight into what's actually going on under the hood. Again, this is work out of DeepMind. That's why we bundle it here. So this fourth part is kind of dedicated to DeepMind. Maybe before I go there, I just want to mention first, I was really impressed by the DeepMind people. So my sort of cookie honey jar interpretation of Google is slightly wrong. I think influenced by Elon Musk, of course. It's nice to see that there's good people out there, and maybe not so good for, let's say, as a Tesla investor, I would like to see them work for Tesla, but or humanoid, or at least SpaceX. But nevertheless, that's a different conversation. I think what happened in this particular case, Google research has been morphed together with DeepMind. So my suspicion is that the DeepMind people are going to take over. Again, saw some really impressive people there, good work, interesting work, and it's good to see that. I think we need competition. We need fruitful competition between the players. We have OpenAI, Microsoft. No matter what you think about OpenAI, the people there and the work that's been done is good. We have Google, which is good. We have Tesla, which is good. So we have three players that are competing with each other, which I think is a good thing. We need more. We have NVIDIA. Within NVIDIA, we had some interesting discussions already about what they did. I think they were present at Neurips, and there's some good people there. And when I say good people, by the way, who am I to judge whether somebody's good or not? I judge the output and also the enthusiasm and the energy. To be fair, the Google DeepMind people, I think, were a little bit less energetic. I think the merger is creating some insecurities there, which is normal. It's human. But nevertheless, again, for all the listeners, hopefully some of you guys are part of the DeepMind team. I'm really impressed, and just keep on with the good work. This is the Not Even On podcast. It's December 25th, 2023. This is Krim Delco. Since the last update, we're down 1.7%. The market is up 20 basis points. For the year, we are up 120.8%. The market's up 23.9%. We're up from about 96.1%. So let's start with the conversation, part 4 in Neurips. Let's start with Promptbreeder. So Promptbreeder is a general purpose self-referential self-improvement mechanism that involves and adapts prompts for a given domain. This is a bit of a mouthful maybe, but let's step back a little bit, okay, and think, what does this actually mean? By the way, Yannick did a video on this just 2 months ago, as usual, recommended. We can go back to Gödel and Turing and these people, right? So there is this evolution in computation and theory of computation, today called theory of computer science or theoretical computer science, but let's not get boggled down with words and university departments here. Let's just think about first principles, right? We have a Turing machine, which is based on von Neumann model, input, output, code, memory, all that stuff. And that machine can, in principle, execute a lot of things, not everything, but whatever's allowed under the laws of physics, plus has certain properties. It can be expressed in a way that can be computed, and it can be expressed in a way that functions can be expressed, and then that can be used for computation. So things along those lines. So whatever can be expressed within this context can fundamentally be used as computation, and therefore also executed on a computation machine. Now, why am I going all the way back to Gödel and stuff? Well, if you want to create an intelligent system, and this goes back to Schmidhuber, and I've been less than impressed with him at Neurips. He gave a presentation. I think he's a bit like Hinton and LeCun. He's a legend, but he's passé, and I feel like he doesn't have the finger on the pulse. And I could be wrong, and I really apologize for that. But anyway, his work in the past was very interesting, and he wrote a couple of papers and books and things like that, and one of them is the Gödel machine. And I think that's really interesting. What is the Gödel machine? It's a machine that, in a sense, is self-referential, right? It's a machine that takes a goal and sort of, in a self-referential way, improves its own code and its own mathematical approach to solving that problem. So fundamentally, it has a meta improver. So it is not just improving the path towards the solution, but it's also improving the improver. And this is kind of the fundamental idea of Promptbreeder, right? You have, now we're in 2023, right? So let's fast forward. We have this mechanism where we use a large language model to generate a prompt with a certain goal in mind, and then that prompt gets evaluated. Other prompts get generated, and then we have a sort of a evolutionary algorithm. Evolutionary algorithm means we have a hereditary, variational, and selective process here. So we have a couple of prompts, let's say 2 prompts, and then they get evaluated based on whether they can execute a certain task or get us to a certain goal. And then the better one gets chosen, and then that one gets evaluated against the next one, and so on and so forth. Now, what Promptbreeder has is also the the chooser or the improver itself, so the meta improver, or that thing which actually decides whether one prompt's better than the other, that thing gets also improved. In that sense, if we want to use some other language from reinforcement learning, what we have here is a reward function design and also a reward function evolution, right? So we're not just using reinforcement learning here or some sort of derivation of it, we're also improving the reward function. This is, I think, fundamentally what's going on here. They're not using that language, but if you ask me, this is really what's going on. And it's really fundamentally based on these works by Gödel and Church. And I think it's interesting because to me, this is the path towards intelligence. Whether it's artificial, general or not, I don't care. That's what intelligence needs to be. It needs to have this ability to generate its own path towards solutions and then improve that path. And that's what I like about Promptbreeder. This is really, in a nutshell, all I want to say here. There's a lot more to say. You know, let's say the Gödel machine is a type of self-referential universal problem solver. Its design is inspired by Gödel's incompleteness theorems and the Church-Turing thesis, which asserts the equivalence of different models of computation. The goal of the Gödel machine is to create an artificial intelligence system that can learn to perform any task that is computationally feasible. We talk about universal problem solver, self-improvement, self-reference, learning from experience. Again, nothing really earth-shattering here as far as you know, the approach is concerned. You can even say this is classic you know, machine learning, things like that. But what I really like about the idea is just this self-referential improvement, and that the improver improves through learning. So you're parameterizing not just the prompt engineering, but also the selection process of which prompt is being chosen over another. Next, let's talk about Self Debugger. There was a presentation by a lady from DeepMind. Now, the idea here is teaching a large language model to debug its predicted program via a few-shot demonstration. The goal here is to have code generation by large language models and then self-debugging. Now, this is of course in the same, I would say, family like the Promptbreeder, because what you have here is, again, a self-referential system which improves itself. Now, this is not as meta as the Promptbreeder, in a sense that I would say it's a little bit more down to earth. All it does is it looks at a you know, let's say the large let's call it the foundation model. Let's not get boggled down with large language and all that. Let's just I'm just call these things foundation models from now on. And the foundation model has the ability to generate code. That code can be right or wrong. And how about we find a way to automatically self-improve the code? How can this be done? It can be done in many ways, of course, and there's lots of work and lots of references. And what they mention here is the debugging process is reminiscent of the rubber duck debugging for human programmers. What they refer to here is an idea that goes back to a book written in 2000, which is that when a programmer writes a program, she often tries to explain the program to a rubber. Forget the rubber duck; it's just some symbol. Imagine you have a thing or a person or something in your mind. You're working by yourself in your office. You're programming, but you're talking to this imaginary thing, explaining the thing, what you're trying to do with the program. That's the whole idea of rubber duck programming, and that's what these people are trying to do. Use the language model to explain what the program is supposed to do, and then while it's explaining, catch whether the actual program that has been written does what it's supposed to do, and if not, improve it. This is the fundamental idea. I really find this powerful. And again, there's this self-referential process here, which in my opinion is just really fundamentally very interesting and strong and should be pursued. Next, I want to talk about chain of code. Now, what is chain of code? This is, it's another, I'm not even sure if this is a paper that was presented at Neurips, but it's related to the debugger, which again was a big, it was an invited talk. It wasn't just a presentation or a poster. So that's why I also called on it. I just feel like, so what's chain of code? Anyway, chain of code is, the idea of chain of code is that you have sort of in the family of the chain of things, right? We have chain of thought, which by the way, I should have mentioned in the Promptbreeder conversation. What is chain of thought? Chain of thought is kind of like a sequence of prompts that are mimicking a chain of thought, and Promptbreeder is just trying to automate that and make those chains better. Chain of code is a similar idea, but here we have certain particular problems that a prompt if you ask a foundation model to do something, for example, to tell me, here's a text, please tell me how many times the author is using sarcasm, right? This is a problem that chain of code can actually solve better than maybe other types of approaches such as chain of thought. How? Well, you could have, you could actually write code in the foundation model which defines what is sarcasm, and then you just, you know, develop a counter and count that thing in the text. So instead of having the foundation model get to the right answer directly, you could use this chain of code approach, where again, you write a script where you say, look, this is a text, and please write me how many times is sarcasm being used. And you know, you could use, obviously you can see the use for this. You could have sentiment analysis in an article, sentiment analysis in a book, sentiment analysis on Twitter or X or whatever it's called today. Like this can be used for that, and the way you would do that is, you know, functionally is you would say, I want to see how many times is sarcasm being used, and here's the script for that. Please follow the following script. Sarcasm is defined as following, and you just write this chain of code, literally a chain of code, which I think is, again, of course you could add the sort of self-improvability here, where the code itself could be debugged by the self-debugger or even improved by some Promptbreeder approach. And again, this is work out of DeepMind. What I find fascinating here is the ability to dissect the problem into more granular steps that then it can be either improved or at least better debugged. Next is FunSearch. This is a project also out of DeepMind where the system is trying to evolve better functions to solve a problem. A canonical problem such as the bin packing problem can be solved by iteratively try to find functions that can solve that problem. What does that mean? This is again in this context of self-improvement and iteration. It's solving really complex problems like the bin packing problem through an iterative approach where the language model develops functions, literally functions, mathematical functions that then are evaluated against certain criteria and improved. In the paper, they mention, we note that FunSearch currently works best for problems having the following characteristics: A, availability of an efficient evaluator; B, a rich scoring feedback quantifying the improvements as opposed to binary signal; C, ability to provide a skeleton with an isolated part to be evolved. For example, the problem of generating proofs for theorems falls outside the scope since it is unclear how to provide a rich enough scoring signal. So let's parse this a little bit more. So what they're saying here is that this FunSearch idea, which is that the large language model or the foundation model is trying to evolve functions to solve a problem. So instead of solving the problem just like sort of in a black box way, it's iterating in function space to get to the solution. And in order to do that effectively within the FunSearch context, we need to have an efficient evaluator, i.e., remember reward function design. So we need to have a good reward function here. And we also need to have rich scoring feedback, quantifying the improvements. So this is sort of saying that for now, at least, FunSearch is not sort of in the family of reinforcement learning, where the reward function is one last sort of big success versus all these paths towards there are not known. That's not a good application to FunSearch. FunSearch requires a more step-by-step approach towards the solution. Now, this might sound a little bit like a tautology. Like if I have a problem that can be dissected into many small steps, and all these steps can be evaluated properly and scored properly, then that's kind of a good problem to have in the first place. And algorithmically, I will solve that one way or the other. So FunSearch is just sort of one application of that, but I still think there's a little bit more depth here than just saying something obvious just in another fancy way, right? We could use reinforcement learning for this. We could use probably many other older aspects of neural learning and things like that. Nevertheless, I think there is a bit more depth here. Like take the concept of Kolmogorov complexity, right? Kolmogorov complexity, which kind of defines the complexity of a problem as how many lines of codes do you need to write to solve the problem. And in this foundation model world, you could end up having things that look very complex, like bin packing, turn into pretty low Kolmogorov complex problems, because you only need a few lines of code or a few prompts that can solve the problem. So then the question comes, what is actually Kolmogorov complexity, and how do foundation models change it, and why is that so, right? Those are very interesting fundamental philosophical questions. What does it mean to be complex in the world of foundation models? Well, if you think about it, foundation models are just a compressed representation of knowledge, and we can prompt that knowledge and prompt it to do function search and then solve very complex problems. So do we have Kolmogorov complexity here? Is a problem still complex if a few prompts or some chain of code or chain of thought can solve it? Is holding an egg a lot more complex than the bin packing problem? And these are open questions. I would say that complexity has to be rethought, because cognitive complexity tends to be less complex in the world of foundation models, and dexterous, low-skill, physical interaction type complexity tends to be more complex. Those are interesting questions that I don't think I have an answer here, but I think they're opening themselves up for really interesting conversations. Next, I want to talk about the robotics presentation that DeepMind gave at Neurips, and here's the three big conversations: RT1, RT2, and OpenX data set. Those are, in my opinion, really important projects. Again, show the long-term vision of DeepMind, which I think is important. The idea is to build a transformer architecture for robots. So tokenize the action space of robots, and then use transformer based architecture, self-attention algorithms or things along those lines to to try to generalize the robotics task. This is fundamentally what RT1 and RT2 and then OpenX, which is a data set supposedly supposed to help cross-embodied data set. This is the key. So you can use data across different types of robots, because what do we have in the robotic space as opposed to the language space? Of course, we have that the actual embodiment is very different. The data is read through a camera on a robot which is 1 meter tall versus 30 centimeters versus a drone versus a humanoid versus blah, blah, blah. It's very different. So we have different perspective, has different, an X, Y, Z coordinate means different things to different robots. How do we solve that problem? OpenX solved that problem through normalization, through encoder decoder type technology. So you can sort of have take let's say 10 different robots in 10 different environments, collect let's say have an ego camera that looks how the robot slices an orange or an apple, and then normalize that data so other robots with different arms, different actuators can still use the data. This is the idea of OpenX. RT, again, RT is the architecture, OpenX is the data set. I think I don't want to talk too much about this here because I think I could talk for hours. I mean, this is really interesting, but I think fundamentally what RT has done, I think it has proliferated the idea of transformer architecture in robotics. I've seen that in Jitendra Malik's work, in Sergey Levin's work. A lot of the Stanford people use it. This is sort of my world here. I'm sure other people use it also, so I don't want to diminish other people's work. I'm just saying in my circles here that I follow and that I am exposed to at Stanford, that's what I've seen, and I think RT1 and 2 have definitely laid the foundation. I don't know what inspired what, and if I can really say that, let's say, DeepMind inspired all this work, but I think the usefulness of transformer architecture in robotics to me is obvious. You can use it like Shuren Song is using, for example, this sort of foundation model approach towards at least high-level planning, but we can also use it for the low-level stuff. And this is really I think the holy grail, right? Can we use transformer architecture in robotics with 4D data, so X, Y, Z and time, and use same self-attention mechanisms that we've been seeing used in language models, and make some progress. I think OpenX, just to finish this conversation about the robotics team, very, very important stuff. X embodiment just means that we have different types of formats of robots and data collection formats that then get normalized and that can be reused in other, let's say, in other robotic environments. The key, again, OpenX is starting a new line of research on open embodiment, and hopefully this will generalize into scaling robotics, because the fundamental problem of robotics is the scalability, the bootstrapping problem. How can we get a fleet of robots out there that start collecting data and learn from them? And for that, we also need to have a data set that is already architected in a way that we can collect from, future humanoid robots at Tesla, humanoid robots at other companies, the Google robots. How about we learn from the cars, self-driving cars? Can we translate the learning into the humanoid robot? This is what Tesla is doing, or at least claims to be doing. So those are interesting approaches, and they also go back to the data collection. That's what OpenX, in my opinion, is trying to achieve, and that's why it's so powerful. The self-stated goals of OpenX are: number one, demonstrate that policies trained on data from many different robots and environments enjoy the benefits of positive transfer, attaining better performance than policies trained only on data from each evaluating setup. And second, provide data sets, data formats, and models for the robotics community to enable future research on X embodiment models. So what they're saying here is, again, a lot more depth here than one might think on first sight. They're saying that if we have 5 robots that each learn a specific task within their own lab, what they're saying is that if we could normalize the data of those 5 robots and then train each robot to learn all these tasks, that even those individual tasks would be better. There's some sort of transfer learning happening. This is really powerful. And again, opens up a whole new line of research, which in my opinion is just really very powerful. And now the last, but certainly not least, presentation I want to discuss, and I really apologize for the length of this episode. I just wanted to pack DeepMind into one episode, and having 30-something minutes talking about probably the most important AI company in the world is not even doing enough reference to the importance of this work. But the goal of the Not Even Known podcast is to give people a sense of what it feels like to run a hedge fund. And one of the sub goals is also to keep it sort of palatable, usually between 15 and 20 minutes and not an hour or something. But it is what it is. And I'm going to therefore extend this one a little bit more. So this paper, Understanding Diffusion Objectives as the ELBO with Simple Data Augmentation, Evidence Lower Bound, that's ELBO. Now, this is, in a sense, pretty technical. In a sense, it's not very technical. A lot of the AI papers, the foundational papers, the mathematical papers, they remind me of economics in the sense that there's a lot of math here and a lot of gibberish about matrix math and all that. It's not very hard, okay? Math is not the problem in AI. What the problem in AI is actual implementation, hardware, memory, writing that stuff, debugging. It's very dirty, hands dirty type work. This is not quantum physics, and the math is not so hard. It reminds me of economics because that's what we had in economics. We had all this complex math, and as economists, we were always intimidated by it. If you're an undergrad math major, you can walk into AI and do pretty well, at least on the math side, right? And that's not going to make or break your career. What's going to make or break your career is the ability to code, throughout a night on 2 slices of pizza and debug that problem and solve that problem, and maybe find a way to repurpose this GPU or whatever you have, or maybe write a library for the TPU that allows the compiler to actually take advantage of the acceleration, like the really nitty-gritty engineering work. That's what AI is all about. But every now and then there's research and theoretical stuff that's really important, and this is one of them. So this ELBO stuff, what is it saying, right? It's looking at diffusion models. Background, diffusion sort of introduced by several people. Again, my reference here is Stanford, and I apologize if I'm too Stanford focused, but Stefano, Hermon, and all introduced scoring function to diffusion models. Their framework, score matching, refers to training a neural net to estimate the score function gradient of the log density of the data distribution. This provides the vector field that their generative modeling framework uses to produce samples using Langevin dynamics, whatever that is. Let's not go there. What is Hermon doing? He's saying, look, let's look at physics. And that's a paper from a couple of years before that. You drop a stone on a piece of stone, a hot stone on the floor, and the heat will dissipate in a certain way. You drop a drop of water on a pond, the waves will dissipate in a certain way, so on and so forth. Like we can imagine that. Now, how about we model that sort of in a step-by-step way, and we give we compartmentalize the whole thing, let's say in small batches, x, y, z coordinates, and we give each batch a little vector, and that heat or that force or whatever we're trying to model dissipates and we just represent that dissipation in these little vectors. They have direction and force, I mean size, right? And now let's go into the image world. Take an image and take a cat, image of a cat, and add random noise to it. How do we add random noise to it? Well, we take the cat and then we keep adding random noise to it, whatever that means. There's something called a kernel, which again takes each pixel, let's say in 2 dimensions, x and y coordinate, has a little vector that adds a little bit of noise each time step until we have completely noisy picture. And now we can denoise that, because how about we remember how we added all that noise? Now we denoise that thing. And we denoise that thing by reversing that process, and then we get the cat back. We do that 10, 50, 100 million times with different cat pictures. We kind of learn how cat pictures are noised and denoised. That's diffusion. So these little vectors, each little data point has a certain noise to it, and we can kind of learn how much each data point contributes to the full noisy picture, and then by denoising we just undo that and get back to that little data point, and we just learn, we parameterize that, we learn how cat pictures are, what is sort of the foundation of a cat picture. And this is what this paper is saying. This paper is saying that in a nutshell, diffusion is kind of the same thing like probabilistic modeling. What's the probability that certain data points of a cat picture will be there versus others won't? Or if I observe a data point, what is the distribution of that? Like, where does this thing belong to? And an ELBO, the evidence lower bound, is just, okay, well, if we have, we don't know what all the possible distributions of cat pictures look like, but we have a good sense for what they do look like based on our training set. And from there, we can infer that if we have a completely random picture, we can then kind of infer where each random pixel, whether it belongs to that data set or not. And kind of do the same thing like denoising by estimating which of those random pictures in that fully random picture belong to the cat and which don't, and then just pick those that don't, and hence, voila, we can generate a cat picture. This is the fundamental idea. Now, I am pretty sure people haven't read the paper, or people who aren't familiar with probabilistic modeling and diffusion models probably don't know what I'm talking about. Now, I really apologize for this, because what I'm saying here is not that complicated. What I'm trying to say is that you can approach a problem from 2 different directions and get to the same result. And knowing that this problem can be approached from 2 different directions, get to the same result, that means that the 2 different directions are kind of the same thing. And to me, that's really powerful. It opens up new possibilities of research, of just solving the problem, let's say, of image generation, which is obviously a very interesting field, lots of economic value, lots of potential economic value here. We can also use the diffusion model for, let's say, path planning and robotics. So diffusion, I think, is not going to go anywhere, but it's not the only game in town. Maximum likelihood estimation, which is kind of what ELBO really is, which is just, again, you look at certain data points and you try to think, okay, where do these data points belong? What kind of, is data point X, does it belong to a cat, or does it belong to an electric guitar or a mountain, or what is it? And the probability that this belongs to a mountain is high, so let's kind of keep it, and let's iterate over that and see, maybe it's still, it ends up, yeah, it is actually part of a mountain, or no, it's not, I was wrong. So that's kind of what this paper is saying. Yeah, I think it's just some nomenclature here the gradient in a diffusion model represents the vector of partial derivatives of with respect to each component in Z. In simpler terms, it tells us how the logarithm of probability density changes as each individual component of Z changes. So we have certain data observations, and how much do they contribute to the actual picture. What is the probability that they contribute more or less? That's kind of what diffusion is trying to estimate. The gradient of the logarithm is particularly useful in probabilistic modeling and machine learning. It appears in various contexts, including maximum likelihood estimation and gradient-based optimization. A high positive value in the gradient indicates that a small change in a particular component of Z will significantly increase the likelihood of observing Z. Conversely, a high negative value indicates that a small change will decrease the likelihood. In some contexts, this gradient is often referred to as the score, or the score function. It quantifies the sensitivity or log likelihood to changes in the parameters. That's why it's called scoring. Score matching function takes as input a data point Z and produces a likelihood that this Z is part of the target data distribution. Key advantage of score matching allows direct gradient estimation without needing to estimate potentially intractable normalization terms required for density estimation. So that's kind of the paper. I think, again, what's really powerful here is that you have two different approaches, which at the margin are kind of the same thing, but this is why engineering is so crucial. Even though there might be, in principle, the same thing, fundamentally, they're not the same thing. And when it comes to engineering, maybe diffusion is better than maximum likelihood in certain areas. Just as a sort of tangent here, this is very similar to the bin packing problem in FunSearch. FunSearch is different than quantum computing, but the bin packing problem was tried to tackled by both. The quantum world is trying to tackle it, and the FunSearch world is trying to tackle it. So that tells me that in a nutshell, those two problems are the same problem. So to summarize part 4 of the Neurips conversation, I spoke about the Promptbreeder by DeepMind, the Self Debugger, chain of code, FunSearch and Robotics. The Robotics team, really amazing work in RTX and OpenX, and then finally understanding diffusion objectives as the ELBO with simple data augmentation. Also, all this work is from DeepMind, and I think DeepMind has really been very inspiring here in Neurips, and also encouraging to see that there is a lot of talent out there and there's competition, and this will proliferate the field. Thank you.